So hello everyone. We're starting off with the 2018 Provincial Co-op problems. And starting with question 1, if you need to read a question, pause the video here. And so the key point here is to notice that the number of students in a class has to be an integer, and so this will limit our solutions. So first, let's say let t be the number of students in the line in total, and let a be the number of students in class A. Then we can say that since a fifth of the students in a line are in front of class A and 12/17 are behind, we have 1 minus 1/5 minus 12/17 of the students in the line are in class A. And so we can say that t times this is equal to A. We can simplify this to 8 over 85, t is equal to A, or 8t is equal to 85A. Now we're looking for an integer solution of A between 20 and 30. So one way you can do this is by simply checking all of the possible values and see which one works. Alternatively, you can see that since 8t is equal to 85a, 85a must have a factor of 8. But 85 does not have a factor of 8. That means that a has to have a factor of 8. And 24 is the only number that satisfies this, and so the final answer is 24. The next question considers a cube. It says that two edges of the cube are said to be parallel if they are parallel on the four-sided polygon formed by their vertices. Pretty standard definition. How many ways are there to choose two edges so that they are parallel? Note that the choice of ABGH is the same as the choice of GHAB. So in other words, order does not matter here. First, I'll just enlarge this cube given here. And alright, so now we have a bigger cube to work with. First, we want to identify all of the parallel lines over here. And let's first say, look at AB. So AB is parallel to CD, and it's parallel to EF and GH. Next up, we can look at BC. And we see that BC is parallel to AD, EH, and FG. And then there's a final set of parallel lines, basically all of the vertical lines over here. And we see that we have encompassed all of the 12 edges in here, and there are 3 sets of lines that within each of these sets, all of the lines are parallel. So now we want to find the total number of pairs of parallel lines. So how would you do that? Obviously, each of these sets of lines are oriented differently, and they're not parallel to each other. And so we only need to look at one of these sets and multiply our answer by 3, since essentially each of these sets are identical. So let's say we look at the red set. There are 4 parallel lines in here, and we want to choose 2 of these lines. And any 2 pairs of lines would work because they're all parallel to each other. And so we can simply say that within the red lines, there are 4 choose 2 pairs of lines that are parallel to each other. And for those of you who have no clue what the symbol means, this is called 4 choose 2. And I'll explain in general what the choose function is. So essentially, if you have m total objects, and we need to choose n of those, then we write M, capital C, N, like so, or some people write it as here. And there are a few other ways to write it, but essentially they all mean the same thing. We want to choose N objects from M total objects, and order does not matter. There is a formula for this, which I'll talk about later on, but even without the knowledge of this, it is still really easy to count how many pairs of lines we have over here. Even the most tedious method, listing all of the things out, wouldn't take too much time over here, right? So we have A, B, E, F, A, B, C, D, A, B, G, H. And then we have C, D, E, F, C, D, G, H. And lastly, we have E, F, G, H. And so we see that there are a total of 6 choices here. And if you know combinatorics, know a bit about combinatorics, then you will know that 4 choose 2 is indeed equal to 6. And this aside, we have the green set and the blue set, and all we need to do is multiply 6 by 3, and so 18 is our final answer. So before moving on to the next question, I will just briefly go over the combinatorics, and this will ease us in our discussion further on. So to start, let's just look at what if we want to choose k objects from n total objects and we don't care about the order. So we write it like this or like this, depending on your method of choice. And we want to see what the answer is. Now, we can think it through as such. If we want to choose k objects, let's just choose them one at a time. So we have k different objects. The order doesn't matter here. We want to choose. So let's look at the first object first. There are n different choices here that we can choose for the first object. And then, since we have chosen one object already, there are n minus 1 objects we can choose for the second object. And then n minus 2 choices we have for the third object, and so on and so forth, until we get to n minus k plus 1. Unfortunately, this is not the complete formula, because some of you might have realized already that we set the first object that we have chosen in the first slot over here. But the choose function does not care about the position of the object at all. And so, since we have taken the position of these objects into consideration here, we're over-counting actually by quite a bit. And so we need to figure out how to get rid of all of these over-counted bits. And essentially, we want to look at, well, if I have k objects, let's just say that these are the k objects, then how many different ways can we arrange the same k objects in different orders? And all that we have to do to get a formula for n choose k is to divide out whatever result that we got here by whatever result we got here. And so how many ways are there to arrange k different objects? Well, there are k objects you can choose for the first slot, and then there are k minus 1 objects we can choose for the second slot, and so on, all the way down to 2 objects for the second last slot, and only 1 object left for the last slot. So this gives the number of ways we can arrange k objects in a row. And there is a shorthand notation for this, and since we're multiplying from 1 all the way to k, every single integer from 1 to k, there's a shorthand for this. It is k with an exclamation mark, and we call it k factorial. And this is really handy because in counting, we encounter a lot of these sort of multiplications, and we can shorthand a lot of these formulas by writing it using the factorial sign. So just as a first practice for using factorials, see if you can figure out a formula using factorials for the formula over here. And the formula over here, if you haven't figured out, is n multiplied by m minus 1 multiplied by m minus 2 all the way to m minus k plus 1. And I'll give you a second to do that. So I'll give the answer around now. So really the key point here is to notice that we basically truncated at m minus k plus 1. So if it is n all the way down to 1, then we simply have n factorial. However, we truncated at m minus k plus 1. And the rest of the terms are, of course, m minus k minus 1, all the way down to 1. But you might notice that this part here is a factorial in of itself. This is m minus k factorial. And so the whole thing over here is n factorial. The blue thing is m minus k factorial. And they're all multiplied together. So all that we have to do is divide n factorial by m minus k factorial. And then we'll get the result for n multiplied all the way down to m minus k plus 1. And now, remembering that we have to divide this result by whatever result we got down here, we get a formula for n choose k as such. So n choose k is equal to n factorial divided by m minus k factorial divided by k factorial, or written using fractions, n factorial over m minus k factorial k factorial. So this formula is obviously needlessly complicated for the question that we just did. However, if n and k are bigger, then this formula is definitely on your side, especially if you have access to a calculator. So just as a practice, in the question we dealt with 4 choose 2, now we could have just counted this as 6. But if you wrote this out, we see that we would get 4 factorial divided by 4 minus 2 factorial, 2 factorial. So this is 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. And after the cancellations, you see that it is indeed equal to 6. So that sums up this tangent on the formula for n choose k as well. Moving on to the next question. This is an expected value question, and it's quite long. So if you need to read the question, pause the video here, and I'll simply begin working on the question. So for such expected value questions, what we have to do is consider each of these subcases, and we have to find the probability that Pam will get the question right, and then multiply that by whatever marks that she would get for answering that question right. And so let's begin. The first set is that Pam knows the answer to 5 of the questions. And so she will definitely get these 5 questions right. And so what we have is 5 questions multiplied by a 100% chance of getting it right, multiplied by 4 marks each. Now we can just leave the 4 marks out for the end, because we know that all of the questions is worth 4 marks. So just leave it as such. And for the next set of 5 questions, she can roll up 3 of the given choices. So what's the probability that she would get it right? Since there are two remaining possible answers, there's obviously a 50% chance that she'll get it right. So it will be 5 times half. For the next 6 questions, she can roll out 2, and so she chooses random from the 3 that remain, and so it is 6 times a third is the expected value from these 6 questions. For the next 3 questions, since there are 4 random choices, there's a quarter of a chance that she will get those right, and there are 6 questions remaining, and there are 5 options left, so it's a fifth of a chance that she'll get those right. And so all we need to do now is to calculate this, and we will get 11.45 as our answer here. Now, we must not forget that each question is worth 4 marks, so we need to multiply this answer by 4, and so the final answer is 45.8. And that's the third question. Okay, moving on to the next question, question 4. Again, if you need to read the question, just pause the video. So we need to go from A to H, and we have to pass through both X and G. So mark out these 4 points over here. And we see that the only way to get to X is directly from A. And since A is a starting point, we must have A goes to X. Next, we can have X going to I and then to G, or we can have X going to C and then to G. And then we have to go to H. So this is the path graph that we have available to us. And then we just need to find a probability at each of these points, essentially. And so we see that from A, there's a third of a chance that we're going to go to X. And then either choice from X to C or X to I works. And so I'm just going to say that this is half and this is half over here. And from I, there is a 100% chance that it goes to G. That's the only path it can take on. And from C, there is a 50% chance that it will go to G. And then from G, the only path that we can take is H. So now what we have to do is basically add up the probability of either of the roots over here. And so we have a third times a half times 1 plus a third times half times 1. And after simplification, this reduces to a quarter. And so the final answer is a quarter. So on to the next question. As usual, if you need to read it, pause the video here. So the key here is that the number is a palindrome. And if we look at the digits that we need to use, there are 4 2s, 4 3s, and 3 4s. This adds up to 11 total digits as given. And we notice that the middle digit must be a 4. And the reason is if it's 2 or 3, then there are an odd number of 2s or 3s remaining, and there's no way that we can balance it out. And so the only way is for the middle digit to be 4. And then whatever that we put to the left of 4 is mirrored on the right side. So really, all we need to care about is what happens on one side of the middle number. And so we have 4 2s left, 4 3s left, and 2 4s left. And so we need to basically have 2 2s on this side, 2 3s on this side, and 1 4s on this side. And so how many ways can we order this? Now, a very categorical way of counting this is to say, first we assume that all 5 of these numbers are different from each other. Of course, in this case, that the 2's are the same and the 3's are the same, so we can deal with this overcounting later on. So there are 5 total numbers, and we want to order these 5 numbers. And the placement obviously matters. So in this case, what we have is 5 choices for the first number, 4 choices for the second number, and so on. And so the answer would be 5 factorial. And now we need to deal with overcounting. So since there are 2 2's, switching their positions has no effect on the result. And so we need to divide by 2 to account for that. And similarly, since there are 2 3's, we need to divide by 2 again. So this will give us the number here, and this will be 30. And so the final answer here is 30. Okay, so the next question says, convert this repeating decimal to a fraction in lowest terms. Now, there is a general formula for this, or a trick. You might consider a trick. But first I'll work through this problem without the trick. So this repeating fraction we see is 0.230769 repeating. By writing this long bar on top, we indicate that this is a repeating fraction with these digits being repeating. And we can figure out this value as a fraction by doing this. If we set this number equal to x, and we multiply both sides by 1 million, and the reason I did that is because now the right-hand side is 230,769.230769, repeating. Now what can we do here? Well, we see that the decimal part of this number on the right is simply x. So if we subtract x from both sides, then we're left with this. And so x is equal to 230,769 divided by 999,999. So the next step here is to figure out how we can reduce this fraction. So what we need to do is prime factorize both of these numbers. And the trick is we can sort of do these two numbers together. So if we write 230,769 and 999,999, and then we see what common factors they share. Now, a good one to try first is obviously 9, because the number on the right is obviously divisible by 9. So the divisibility rule for 9 is we add all of the digits together, and if the number itself is divisible by 9, then the sum of the digits is also divisible by 9. And the other way around works as well. So we add 2 plus 3 plus 7 plus 6 plus 9. That gives us 27, which is a multiple of 9. And so we can divide 9's out from both sides. And we would get 25641 and 101111. We can see that we can divide out another 3 from both of these numbers. And the divisibility rule for 3 is the same as for 9. You add all of the digits and see if that is divisible by 3. And so we would get 8547 and 37037. And basically we need to continue this process. Basically, you will eventually see that these two numbers also share a factor of 37, another factor of 3, and so on. And eventually you will get to a simplification of 3 and 13. And these two numbers share no factors, and so x is equal to 3 over 13, and this is the fraction in the slowest terms. So the answer is 3 over 13. Moving on to this next question, pause the video here if you need to read it. This is a question essentially on setting up a correct system of equations and solving it. So we have two variables here, and I see that we can set up two equations. So the first equation is essentially this sentence here. And what we can get is that there are m over 2 $1 coins and n over 2 $2 coins. And these values combined give us 124. The second equation is a bit more complicated to set up, but essentially what we need to see is that the coins that she used to purchase the gift certificate for her father is the whatever total that she had subtracting what she spent on her mother's gift certificate. And so how many coins did she have left? For the $1 coins, she had m in total, and then she spent n over 2 of those. And so she has this many remaining, and multiplying this by 1 gives us the value for the $1 coins. And similarly, for the $2 coins, we have m minus m over 2 times 2. And so this is equal to 96. What we need to do now is to solve the system of equations. And first, we would probably benefit from simplifying this. So the first equation is a little bit easier to simplify. All that we have is m over 2 plus n is equal to 124. So that's the first equation. And for the second equation, we first need to expand. So we have n minus n over 2 plus 2n minus m is equal to 96. And we can simplify this even further by combining the m's and the n's. And we get that the m's actually cancel over here. And so we get that 3 over 2n is equal to 96. So from this, we can immediately solve for n. N is equal to 96 divided by 3 times 2, and this gives us 64. So n is equal to 64. Now plugging it back into here, we get that m over 2 plus 64 is equal to 124. So this gives us that m is equal to 120. And adding these two up, and we get that the total number of coins is 184. And so that's our final answer. So moving on to the next question, this is a pretty classic triangle existence question, but it's different in that it asks for acute triangles. And so we have to watch out for obtuse angles and right angles, essentially. So we can first draw a few triangles and see if it works. So we know that one edge has length 15, the other edge has length 14, and so this edge is n. So this is a triangle, and it seems to work, sort of. This angle here needs to be smaller. And so we basically reach two extremes, two constraints. And one constraint is when n gets small. And if you get really, really small, then eventually we'll reach this point. And this is not allowed. A right angle is not allowed. We need this angle to be smaller than 90 degrees. And so this is our lower limit. And for our higher limit, we have that if the angle between 15 and 14 reaches 90 degrees, then this is the upper limit. And so basically you want to see what are the allowed values between these two extremes. And using the Pythagorean theorem, we can easily find our limits here. So here we have that 15 squared is equal to 14 squared plus n squared. And so n is equal to root of 29. And so we need n to be greater than this value. And obviously n needs to be an integer. And so n has to be greater than or equal to 6. So we do a similar thing for the upper bound, except that now we have that n squared is equal to 15 squared plus 14 squared. And so we get that n is equal to the square root of 421. 421 is between 20 squared and 21 squared. So our upper bound on this is that n is less than or equal to 20. And now we need to find how many numbers are there for n, such that 6 is less than or equal to n is less than or equal to 20. And we do this by 20 minus 6 plus 1, and so we get 50 numbers. The plus 1 at the end is fairly important. And one way to think about this is if we have 6 is less than or equal to n is less than or equal to 20, and we are only interested in counting the number of n's that are possible, we can subtract 5 from both 6 and 20, and we have that 1 is less than or equal to n is less than or equal to 15. I'm not caring about the n over here because we're just counting the numbers that are available. And obviously there are 15 numbers here. So we always need to remember to add 1 to the end here. And the final answer to this question is 15. This next question is also a classic. If you need to read the question, pause the video here. The really smart tactic to solve this question is to say, well, if this number has a remainder 4 when divided by 7, and so on and so on, what will happen if I add 3 to this number? If we add 3 to this number, then we would have a remainder of 7, or 0, when divided by 7, a remainder of 11, or 0, when divided by 11, and a remainder of 13, or 0, when divided by 13. And so if we call this number n, then we know that n plus 3 is divisible by 7, 11, and 13. This is really handy. And by the way, if you have no clue how I came up with that trick, simply I saw that when I subtract 4 from 7, I got 3, and similarly for 8, 11, and 13 and 10. So that's why I knew to add 3 to n to get my desired result. So moving on, if n is divisible by 7, 11, and 13, n must be a multiple of the least common multiple of 7, 11, and 13. And since these three are all primes, we know that n has to be a multiple, let's say it's k, times 7 times 11 times 13. And so this is equal to 1001k. This is a really good product to remember that 7 times 11 times 13 is 1001. And since n has to be greater than 2018, we have that n is equal to 3003 as our smallest answer. And so the answer is 3003. So what did I do wrong here? This is something that's really easy to miss. And basically, I forgot about the plus 3 that over here. we have that n needs to be greater than 2018. That's still correct. But n is equal to 3003. That's wrong. n plus 3 is equal to 3003. And so this is something that's very easily forgotten. And the final answer is 3000. Moving on to the next question. If you need to read the question, pause the video here. So these kinds of coloring questions, the main point is to notice that any corner squares has 3 faces that are on the outside. Any other edge squares have 2 faces on the outside, and all of the other squares have 1 face on the outside. And since we want to maximize the surface area of the large cube that is red, we want to place as many red cubes basically on the corners and along the edges. And so we need to see how many of these squares there are. And first, the corner squares. There are 8 corner squares. Essentially, they're the squares at the vertices. So we can say that for 8 of these, we have 3 faces on the outside. Now, there are 16 red cubes left. And if you count the total number of edge squares on this cube, you see that there are way more than 16 edge squares. And so we can comfortably say, that all remaining 16 red squares can be put on the edges. This gives us 56 total faces that are red, and the total surface area of the large cube would be 6 times 4 times 4, essentially 6 times the edge length, and this gives us 96. And therefore, the final answer would be the reduced fraction after we reduce this, and we get 7 over 12. And so 7 over 12 is the final answer. Moving on to the next question. If you need to read the question, pause the video here. So the key point here is to say that the greatest common divisor of x and y is 64. So we can simplify this problem by saying let x equal to 64a and y equal to 64b. And a and b are relatively prime. Namely, they share no common factors greater than 1. Then we can say since x plus y is equal to 768, we have that 64a plus 64b equal to 768. So a plus b is equal to 768 divided by 64 equal to 12. And since a and b are relatively prime, there are restrictions on what a and b can be. Now, we want to maximize the value of x times y. And if we have a fixed value of x plus y, as in this question, then without any other restrictions, we want to choose x equal to y equals to half of their sum. This will maximize the product of the two numbers. And in this case, we have a restriction that a and b are relatively prime. So we can't choose a equals to b equals to 6, because then they're obviously not relatively prime. So the best that we can do is for a and b to be 5 and 7. They can be the other way around, but the result is still the same. And so x times y would be equal to 64a times 64b equal to 64 squared times 5 times 7. And this will give us this as our result. And so this is our final answer. Moving on, I will show that if we have two positive numbers x and y, and x plus y is fixed, then x times y is maximized when x equals to y. One way we can do this is by using the AMGM inequality. I will not prove the AMGM inequality here, but for those of you who know what this states, we have that the arithmetic mean is always greater than or equal to the geometric mean. And if you don't know what these mean, then these are basically what they are. So this is the arithmetic mean and this is the geometric mean. And we have that the equality case occurs when x equals to y. I will not prove this here. There is another method that we can use to prove this specific result without using AMGM. And that is by saying, well, if x plus y is fixed, then let's say that without loss of generality, we can say that x is less than y. Because if x is greater than y, then we can switch their roles and it will be the same anyways. Actually, it should be x is less than or equal to y. Then let's just say that the difference between x and y is 2k. In other words, the distance between each of x and y to their average is k. Then we have that x times y is equal to a minus k times a plus k, where a is their average, x plus y over 2. Expanding this, we have that x times y is equal to a squared minus k squared. Now, k here is positive because we defined it as x is less than or equal to y, or non-negative. And so k squared is always non-negative, which means that this is at most a squared. And the equality case occurs when k is equal to 0. And if k is equal to 0, then going back here, we see that x has to be equal to y. And so the equality case occurs when x is equal to y. And so this proves the above theorem. Moving on to the next question. If you need to read it, pause the video here. And for simplicity, I'll simply call Alfred, Beth, and Gamma A, B, and G. And so we want them to be seated together. This kind of probability question, we need to consider how many total cases there are and how many valid cases there are. And so the total number of cases is, well, first, if all 12 people are lined up in a row, then the answer is simply 12 factorial. Since all 12 physicists are considered to be distinct, obviously, and so we are trying to order them, and so there are 12 factorial different ways to do so. Now, however, we're considering them in a circle. You can think of this as wrapping this line around so that the tail joins back to the head. Now, there are fewer cases here because if we rotate the table, it's still the same. It's still considered the same arrangement. And so since we can rotate the table in 12 different positions, we're overcounting this by 12 times. Since there are 12 seats, if we rotate every c over by 1, it's technically still the same arrangement, but along a line, it will be considered a different arrangement. And so we need to divide 12 factorial by 12 to get the number of arrangements in a circular, around a circular table, and this gives us 11 factorial as our total number of cases. And so moving on to how many valid cases there are, we see that since Alfred Bethe and Gamma has to sit together, that means that nine other physicists can sit basically wherever they want in the 9 remaining seats. And so there would be 9 factorial for all of these 9 other physicists. Now, it actually said here that Alfred Bethe and Gamma does not need to be seated in this order. And so we need to see how many different orders we can put Alfred Bethe and Gamma in. Now, since there are 3 of them, and they sit together, and we're trying to arrange them in, the answer is simply 3 factorial. And so our final answer would be the number of valid cases divided by the number of total cases. So you have 9 factorial, 3 factorial divided by 11 factorial, and this gives us 3 over 55. And so 3 over 55 is our final answer. Moving on to the next question, pause the video here if you need to read it. So to solve this question, we basically need to find the area of these 2 shapes. We will derive the general formula for the area of a regular hexagon and octagon here. So first up, let's derive the formula for the regular hexagon of side length A. We can partition the hexagon as such, and we can find the area of each of these equilateral triangles. If the total side length is A, then we have that this edge here is A over 2. This height here is root 3 over 2A. Because this is an equilateral triangle, this is 60 degrees, this is 30 degrees, and so we have a 30, 60, 90 triangle. And so the area of this triangle is root 3 over 4a squared. And so the area of the hexagon is 3 root 3 over 2a squared. We simply multiply this result by 6. Moving on to the octagon, this is slightly more complicated, but we can partition the octagon as such, dividing it into 1 central square, 4 side rectangles, and 4 corner triangles. So if the side length is A, we can see that this edge here must be A over root 2, and so must this edge. This is because this is a 45, 45, 90 degrees triangle. And since we have these side lengths, we can compute the area of each of these shapes and then add them together. So we have that the center square has area A squared. The side rectangles each has area A squared over root 2. And the corner triangles each has area half A over root 2 squared, or A squared over 4. And adding all of these together, we get the total area of the octagon is A squared plus 4 times the side rectangles plus 4 times the corner squares, and we get 2 plus 2 root 2 A squared as our final result. So now we can go back to our original question. In this question, the side length is 1. So this does simplify quite a bit. So let's look at our formula for the octagon first. Okay, so the area here would be 2 plus 2 root 2. And we subtract off the area of the hexagon, which is 3 root 3 over 2. And in the co-op phase of the contest, we are allowed calculators. So by punching this into a calculator, we get that our final answer is just around 2.23. So the final answer is 2.23. Moving on to the next question. How many integers greater than 9 have the property that their decimal digits increase as you read them from left to right? And they have kindly given some examples. So this might seem a bit difficult to approach at first, but the big hint here is that once you have chosen your digits for a number, there is only one way to arrange these digits such that the digits are non-decreasing from left to right. So for example, if I've chosen the digits, say 3, 1, 9, 7, 5, 7, 2, and we see that the only way to arrange these digits so that it's non-decreasing is first with 1, then with 2, then with 3, 5, the 2 7s, and the 9. And in this case, the question is even simpler because we need the digits to increase as you read them from left to right. So that means that a digit cannot appear twice. So instead of this, we can simply say, well, there are nine things we can choose from. And we can choose any number of them and any one of them, but once we've chosen them, there's only one way that we can arrange them. So as a final example, we say we choose 1, 3, 4, 6, 7, and 9. Well, the only way to arrange these digits so that it's increasing is 1, 3, 4, 6, 8, 9. So how many different ways can we do that? Well, this is essentially a counting problem, and to count the total number of cases, there are two different ways. One way, the much simpler way, is to say, well, we can choose or not choose the digit 1. We can choose or not choose the digit 2, and so on for the remaining cases. So that means that there are two options. We can either choose or not choose 1. There are two other options if we choose 2 or not 2, and so on and so on. And we multiply all of these together. There are 9 numbers, so this is equal to 2 to the 9. And so we get 512. The other not so direct way is to say, well, the numbers have to be greater than 9. So that means that we have to begin at choosing 2 of these numbers. So from the previous problem, we can write this as 9 choose 2 plus 9 choose 3. So this is for choosing 2 of the numbers, this is for choosing 3 of the numbers, and 9 choose 4, and so on, all the way to 9 choose 9. And we will get a final answer of 502. So wait a minute, we got 512 last time. And that's because I didn't actually finish with the previous counting method. We got 512 because we got this from 2 to the 9. But there are several cases that do not actually work, because when we're counting this, we didn't factor into this account. And so how many cases are there extra? Well, one of them that is obviously wrong is choosing none of the numbers. That is obviously wrong because, well, we don't even have a number here. And so we need to subtract of 1. And then, since we can't choose any any one of these digits, since the non-integer has to be greater than 9, we need to subtract of 9 other cases. So we indeed get 502 as our final answer. This method is still recommended because if we're going to add up 9 choose 2 all the way to 9 choose 9, it's going to take a lot of computation and a lot of time. And so this method is definitely recommended. And so the final answer is 502. As a bit of a side note, some of you might have noticed that if there are no restrictions on if the number exists or not, or if the number is greater than 9 or not, then we would simply have that 2 to the 9 is equal to 9 choose 0 plus 9 choose 1 plus 9 choose 2 all the way to 9 choose 9. And this is indeed correct. If you compute this, it comes out both sides equals to 512. Now you can simply show this fact from the problem that we just did. Simply get rid of the restrictions and you will have this result. There is a much more generalized result, but it follows from essentially the same idea. So instead of saying 9, we can just say n. So we have that 2 to the n is equal to n choose 0 plus n choose 1 plus n choose 2 all the way to n choose n. This fact always holds. And we can prove this by a similar argument. So say that there are n different objects and we can choose any number of them, and we want to see how many different ways we can do that. So we have the object called 1, the object called 2, all the way to the object called n. So how many different ways can we select any number of these objects? Well, one way to say is we can pick out A or not pick out. We can pick out 1 or not pick out 1. We can pick out 2 or not pick out 2, and so on all the way to n. We can pick out n or not pick out n. Then we would get the left-hand side of the equation, because it would simply be 2 times all the way to the last times 2. Another way we can do this is by saying we can choose 0 of the objects. And this will give us n choose 0 ways to do so, which is 1. And next up, we can choose 1 of the objects, and we get n choose 1. And so on until we choose n of these objects, and we get n choose n. And we simply add all of these numbers together, and we get the right-hand side of the equation. And since these two things, 2 to the n and the sum on the right, are counting the exact same thing, they have to be equal. So this is the general theorem that 2 to the n is equal to n choose 0 plus n choose 1 all the way to n choose n. Moving on to the last problem in this set. Pause the video here if you need to read the question. The general way to approach these questions is to break down the shape into various constituent shapes, and by adding and subtracting these shapes, you can get the overall area. So for example, here we want to get the total area over here. And so what we can do instead is we can find the area of the central square. Then we can go ahead and find the area of these 3/4 of a circle, and then we can subtract off 4 of these sections here. So we need to find the area for each of these. Now the area of the square is simply 1, and the area for each of these is 3/4 pi, since it's 3/4 of a circle of radius 1. The tricky one is to find the area of one of these shapes. Now we can further break this down into various shapes and calculate the total area from there. So what we can do instead is say that there is an equilateral triangle in here, and it is equilateral because we have one circular arc that's like this, and another circular arc that's like this, and so these three side lengths must be equal. And so we have an equilateral triangle, and after finding the area of this, we're still left with these two bits over here. And so how can we do that? Well, if we look at one of these fans, we see that it is essentially the area of this slice over here is essentially the area of the fan subtracting the area of the triangle. And so this area, the orange area in total, is equal to the area of the triangle plus 2 times the area of these slices. And each of these slices is equal to the area of the fan minus the area of the triangle. So we simply have 2 times the area of the fan minus the area of the triangle, give us the area of this weird shape. So what is the area of the fan? Well, we know that this is 60 degrees. And so this is 1/6 of a circle, and the circle's radius is 1. So this is simply equal to pi over 6. And there are 2 of those. And we subtract off the area of this equilateral triangle, which is √3 over 4. So this gives us the area of one of these weird shapes. All we have to do now is add up all of these various areas. So the total area of this shape is the area of the square plus 4 times the area of these 3/4 circles minus 4 times the area of these weird shapes. And this is equal to 1 plus 3 pi minus 4 over 3 pi minus √3, or 1 minus √3 plus 5 over 3 pi. And using your calculator, you see that this rounds to 7.97, which is the final answer.